Let us test our derivation of computing the backpropagation for convolutional operation. And first, let's try to propagate the, uh, the gradient of the objective function to the input of the convolution. So in the above, we have computed the convolution of A with a kernel K to output and output array B. And here, for example, let us say the objective function is computed by the element-wise sum of B times another random array W, and that setting is not very much different from the actual when the result is actually used in neural networks. We can often, after all the convolutions are done, we will take the output tensor or array and just put all the elements together into a long vector and do the normal multi-layer perception like neural networks again, and that will corresponding to multiply, do the element-wise weight of the B and take the sum, and so on and so forth. So let's just use this as L, and here, of course, that will mean that the gradient of L will be, with respect to B, will just be the same as the element of W, because when you multiply each element Bi with other element Wi, so if you change Bi by epsilon, the object function will change by epsilon times Wi, which means the derivative of this element Bi will just be the same as W. So here is the code implementation, and let us just in this video to set up the problem correctly. So we allocate another random weight matrix of W, and we take the L as just above discussed. And here, by analysis, we see dB will be just W. And here notice we will use this kind of technique over again to verify that our analytical computation of the derivative, element-wise derivative, that is the gradient, is correct. So this is not used in actual neural network model training, but we will use that to verify the computation. We'll allocate a zero matrices just as the same shape as the analysis, the output, and we take some epsilon, and then look, this is of the shape of 3 by 4. We just take every single element, and we keep a copy of that. Notice that convert just to convert this element from a tensor element into a float number, which means we take a copy of that. Then we change the element with by an amount of epsilon, and then we recompute a new object function, and we then consider the numerical difference of the new object function and the original one, and how that is compared, how that is compared to the epsilon, and we use that as a numerical derivative of the objective function with respect to the corresponding I and J element. So after that, we put it back, put the original value back to the corresponding element, and after all the computations, we will check if the numerically computed result is the same of the analytical result. If it's the same, which means our analysis is correct, and we can keep this analytic derivative in the training process and get a view of that, so of the numerical computation. Okay. So well, you can see that they are the same, and if we run it again, still the same. And let's change the random seed so that we have a different setting. So that is correct. Okay. On the other hand, for example, if we take the square of that, you will see that this analysis is no longer correct, and we will have discrepancies of this. How about let me to define the object function. So that will be that with, okay, let's call that LB. So which emphasize that this accept B and only consider the contribution of B of the object function. Take that. Okay. So now we have B, and we have this L. It's taken using the original B, and we use this. Let us see. Now they are different. Okay. And of course, we know that this will not be the W alone. If we apply our knowledge of taking this kind of square functions derivative, we will make up using this and times, I think, 2. Let's try. Now look, the analytical result is consistent with the numerical one. There are small differences, but that's okay. That is mainly because when we take the derivatives using limited step size, this is not the same as the analytical answer as if we can take infinitesimal steps. We can take a smaller step, see if it works, but a slightly improved maybe. Okay. Okay, now we have introduced the idea of the derivative of B, the output, and the verification. And in the next, we're actually starting to compute the derivative of the input.